Hello, friends. This is Miss Adams from Flamingo Math. Welcome back to day 2. We're still continuing our discussion on vectors today. Just want to remind you that when we have operations with vectors, numbers are referred to as scalars. And the scalars in this curriculum will always be real numbers. And in this lesson, we're going to explore sums and products that involve vectors. We're going to look at 2 basic vector operations, vector addition and then scalar multiplication. When we add 2 vectors geometrically, we can either use the head to tail method or the parallelogram method. And if we want to change the direction or the length of a vector, we use a scalar multiple. Let's begin. First, we're going to look at tip to tail method. So you can see here the position of vector u starts over here at this point on the left and goes in a downward fashion. And then vector v, the tail of vector, the tip of vector v is on the tail of vector u. And then it goes up and to the right. So if we want to show the sum of vector u plus v, then that would occur at the diagonal from u over to v. This is the sum of vector u plus vector v. We found it from the initial point of u to the terminal point of v. The parallelogram method, we're going to take vector u here and vector v in the opposite direction. We're going to move vector u up here at the tip of vector v. So how does that look? That vector u went 2 up and 4 right. So 2 up and 4 right puts the end of vector u right there. Vector v is going to go from the tip of vector u over here to create a parallelogram, and then the sum of the 2 vectors is the diagonal going across there. This is the sum of vector u plus vector v. So the tip to tail method or the parallelogram method are both appropriate ways to add vectors together. When we perform addition or scalar multiplication on vectors, we have the components u1, u2, and v sub 1, v sub 2, and we're going to call k a scalar, and it's going to be a real number. The sum of u and v can be found by adding the first component of u and the first component of v, and then the second component of u and the second component of v. So this will give us the new coordinates for the sum of the 2 vectors. And the scalar multiple, we take the scalar real number k times vector u. So you can rewrite that ku as k times component 1 and k times component 2 to get that scalar multiple. So let's look at that from a practical point of view. If you have vector v shown here on the left, this is vector v, and we want to show what the opposite of v looks like, then that's just a matter of taking the vector and having it go parallel in the opposite direction. If we want half of vector v, that would be like that, and then negative 1.5 v. So there's negative v, and negative 1.5 v looks like such. So drawing them is easy using tip to tail or parallelogram method. For example 7, we want to use the vectors to label each one of the following. So negative w is up here. This is the negative, the opposite direction of w, vector w, because w is going up and right, and the opposite would go down and left. Now for v minus w, we have v going this way, and the opposite direction of W. So from the tip to tail method, starting here at the beginning of V and going up to the tail of the opposite of W, this side would be V minus W. So I'm adding V plus the opposite of W. This is V minus W. They both start here and terminate here. Starts here and terminates here. For example 8, we want to find 2 times V, so 2 is a scalar. So 2 times vector V, -2, 3, and then we're going to add vector W, 2, 4. So the components are -4, 6, and we're going to add the components to W, 2, 4. We're adding -4 and 2, so the first components of both vectors and then the second components of both vectors gives us -2, 10 for the sum of 2V plus W. For W minus V, if W is at 2, 4, those are our components, and we're going to subtract vector V, -2, 3, then we have 2 minus -2 and 4 minus 3. So 4 and 1 are the terminal points for the W minus V vector. In number 9, we're going to use components to express the sum or difference as a scalar multiple of one of the vectors shown A, B, C, D, E, or F. So B plus E, let's take a look at this. Here we got vector B right here plus vector E would give us, let's see, we can do that algebraically, can't we? Vector B is -1, 0, and vector E is 2, 3. So what does that give us? 1, 3. 1, 3 is vector F. So B plus E is vector F. For A, we have A is 3, 0, and B is -1, 0. When we add them together, we get 2, 0. 2, 0 is going to be, what, 2/3 of vector A. 2/3 of vector A would give us A plus B. F is located at 1, 3, and we're going to subtract vector B. Vector B was -1, 0, so 1 minus -1 is 2, and 3 minus 0 is 3. Oh, 2, 3, that's vector E. Vector E is 2, 3. And then vector C is, what, 0, 3? And we're going to subtract D. So we're subtracting D. D is 0, -1. That puts us 0 minus 0. And 3 minus -1 is 4. So that's 0, 4. 0, 4. We need to get more than 0, 3. So what would do that? 3/4. 3/4 of vector C would give us vector C. Is that right? 3/4 of 0, 4 would put us at 0, 3. Yes, that's correct. So F and then 2/3 of A and E and 3/4 of C are the calculations for comparing those vector addition problems with the vectors that they gave us here for our example. And finally, on example 10, we want to find the magnitude of V and the smallest positive angle theta from the positive x-axis to the vector OP that corresponds to vector V, which is located at -3 and -3 square roots of 3, which is going to be a little bit more than 5, almost 6. So this is vector -3, -3 square roots of 3. This is our terminal point down here. That's representing vector V. Okay? So we know the tangent of theta is opposite over adjacent, and opposite is the length. Let's sketch that in here. This is the opposite length, -3 radical 3, and adjacent is -3. So we got -3 radical 3 divided by -3. That's the square root of 3, and the angle that gives us tan inverse radical 3 in quadrant 1 is pi over 3. But notice we're in quadrant 3. So our smallest angle, the smallest angle in quadrant 3 would have to be 4 pi over 3. And what would our magnitude be? So the magnitude of vector V is -3 squared plus 3 square roots of 3 squared, so that's 9 times 3, that's 27. I'm just using Pythagorean theorem with those two coordinates there. And 27 plus 9 is 36. The square root of 36 is 6. So our magnitude is 6. The smallest possible angle, I see a mistake here, it should be 4 pi over 3, not 4 pi over 6. That's in quadrant 2. So think about this. From the positive x-axis around to vector V, that angle is 4 pi over 3. The magnitude here on vector V, the magnitude is 6. And that's the end of day 2 on vectors. Join me tomorrow for the very last lesson in vectors.